Hi, this clip is the addendum of the previous video Zilog Z80 and Intel 8085 timing part 2. I want to show you how you can use the delay function that we have discussed in the previous section. First, I will present the communication between different devices, and after the demonstration, if you're still interested, I will explain the source code. So, let's get started. So, this is a microprocessor 1 board. The Arduino is connected over ground to the PIO chip, and here is a send of serial 1 to one pin of the channel A of the PIO chip. So let's start the program. 1800. Switch here to the Arduino. So when I type 1, enter, it sends 1, 2, 3, 4, 5, 6, 7, 8, 9, 0. So the NDI Klein computer with the Z80 CPU and an extension card with 4 TTL chips. I use one of them, this one, which is an T74LS374. That's an octal D-type flip-flop with 3 state outputs. So it has 8 inputs and 8 outputs. If you set one input, the output is set and stays until you reset the output. The Arduino here is connected once with ground. Here's another ground just used for the TTL chip, and this is sent from this chip to the serial 1 of the Arduino. So I've entered the program here on the keypad. Let's start the program. Program is running. And here you see here is a serial 9600, but that's a serial port to the computer. So that's a standard serial port, and the serial 1, where the NDI Klein computer is connected with 300 baud serial, 8 bits, parity none, and 1 stop bit. So if I hit 0 here, it prints 0 on the LCD display and also here on the terminal. 1, 2, 3, 4, 5, 6, 7, 8, 9. So the microprocessor 1 and the NDR Klein computer is connected together, once with ground and one with one signal bit. Okay, let's start the program here, and I'm doing the same here. Start. So if I type here, for example, 8, 4, 0, 1, 2, 3, 4, 5, 6, 7, 9, type A, B, C, D, E, F. So here's the Minimax with a power connection, serial connection to a terminal, and here the CPU is directly connected to the Arduino. You have the ground, the send from the Arduino to the serial in of the CPU, and the receive of the Arduino to the send out of the CPU. So this is the terminal of the Arduino. You see here it's connected at 9600 baud. That's a standard serial port USB connection to the Arduino, and the serial 1 is the other 2 pins which are connected to the Minimax 8085 at 300 baud, 8 bits, parity none, and 1 stop bit. So, and here is the terminal of the Minimax itself, the USB connection, and let's reset the Minimax and load the program. It's in the clipboard, so I paste it and starting the the program. If I type here test, you see on the left side, maybe I should enable local echo. So local echo. So now you see what I'm typing here. Hello. This is a test. When I hit send, it's sent to the Minimax. Let's start with the source code of the MPF1, which is only programmed as a receiver. If you are only interested in the 8085 code, you can skip to 25 minutes 18 seconds. I have already covered the PIO in another video. I will put the link in the info box. So here with the exclusive OR, I'm just clearing the accumulator, and here sending to the port channel 01, which means clear the display. Let me explain this. I could use the system function 624, which scans the keyboards and display one cycle. The other one, display until the new key is in. No, he will just wait for a new key and he won't check the PIO. So I can't use that function because execution time is about 10 milliseconds. And that's far too long because with 300 boards, every bit should take only 3.3 milliseconds, and 10 milliseconds is far too long. That's why I program directly. I don't use this here. On the microprocessor 1 board you have an 8255, that's also a PIO chip, and port 01, that's port B, address 01, you can control the display. So you have your 7-segment display here, and the value you send there will light up the different LEDs. If you send a number from the accumulator to this address, it will display the corresponding number on one column. But you have not only on one column, but all on 6 columns. So if you look here, the display has 6 columns, 1, 2, 3, 4, 5, 6. So that number is sent to 01, will be shown on all the 6 columns at once. So you have the same number on all columns. So if you want only to send it to the right column, you have to use the port C, that's the address 02, set it to, we'll set bit 0 to 1, because with bit 0 to bit 5 all the 6 columns are managed. That means if you want to show a number on the display, you have to light up individually every column with a different value. So that's the scanner routine, the scanner subroutine of the system ROM will do this automatically for you. But that's why it takes at about 10 milliseconds. At the same time, it's also scanning the keyboard. They're also connected to the columns, and yeah, at port 0, the rows are connected to the keyboard. So you have to check every row, every column. That's why it takes so long. In this example, I will use only the rightmost column, and I won't check the keyboard. Okay, here I clear the accumulator, send it to the display, which means all the 6 columns are turned off. And here I light up the rightmost column, that's the 1 here. The C That's 8 and 4. Let me switch to the description here. So bit 7 is connected to the speaker. It's turned on when output is 0. That's, I don't want to turn it on. So that's a 1. And bit 6 monitor control break. So it's also 1. 8 and 4 is 12. That's C. So C and 1 for the rightmost bit. Sending it to the port channel 2. So let's go further in the code. Here I'm reading a value from the serial port or the pseudo serial port, doing a filter. I want to keep only bit 0. And here we're waiting until the start bit is received. So the serial line is always up. And if the other device wants to send something, it will start the communication with a start bit. And the start bit is a low for 3.3 milliseconds. That's why we are waiting here 3.3 milliseconds, and that's the same function I have already covered in the previous video. Going up a little bit. Okay, so loading register B for the loop, reading the next value, filtering out only bit 0, and rotate right carry accumulator, so we'll rotate bit 0 to bit 7. And here I will do a rotate on register C, and C is at the beginning is 0. So here clear C, accumulator was 0, so initially C is 0, and doing an OR with C. So the result of C and A is ORT, and I will put the result of the accumulator back to C, and waiting again 3.3 milliseconds, and decrement jump on 0, so we'll do this 8 times. Finally, the least significant bit which is sent first is at the end of the loop here, is at bit 0, and the most significant bit is after the loop at bit 7. After this terrible explanation, I think it's better to show the receive function in the simulator. For that, I don't have a Z80 PIO. I will simulate here on the peripheral devices our Z80 PIO. I will do manually the input here. And the output here, the 00, is just to display the accumulator in binary format. Here it's only in hex. I want to additionally show it in binary. And here, in this example, the remote device wants to send 31. So it will send over the serial line first the least significant bit, so it's just in reverse order. Okay, don't try to explain it, just launch the simulator. So the first value is a 1. I will put a 1 here. So accumulator is now 1. Has rotated it. And the next value is now a 0. So let me put a 0 here. And the next value is a second 0. So 0 is okay. And the next value is the third 0. Then the next value is 1, so we have to put a 1 here. Next value is also 1. And the next two values are 0. I have to put a 0 here. Next value is also 0. That's the last one. And you see result, we have received 31. Here, to do it correctly, we would have to calculate here the cycles and remove it from the timer. But that's you have a certain tolerances within the UART, so we can ignore it. After that, we have to wait for the stop bit, so we will just wait until receive gets 1. Here, loading the received value to the accumulator, subtracting, maybe I should write here, converting from ASCII. Let's have a quick look at the ASCII table, and you see here numbers 0 to 9, the hex value is 30, you subtract 30 from it, it's 0. 31, subtract 30, it's 1, and so on. 39 minus 30 is 9. So from the ASCII value you're getting the number value. I did this because I want to use also the Arduino, and the Arduino is using the ASCII table. So we have to subtract 30 to get the number. Then the calculator result, I will use system Rom function hex 7, which will convert the number to the 7-segment number, so it can be displayed here without to the display. Here I have forgotten to add a delay. So the stop bit takes also 3.3 milliseconds, and after that it jumps back to the loop, main loop, so and is waiting again for the next character. So this is the source code of the NDR Klein computer, and these two lines are setting the serial port, the transmit to 1, which means if the serial port is, the send is inactive, it should always be 1. That's a normal state. So setting accumulator with 1 and sending the accumulator to the I/O port 30. The I/O port 30 is the address of this chip, and this is bit 0 of one of the output ports of this chip. So the next line, this is a system Rom function. This address clears the screen, and this address waits for a key and retrieves the key to the accumulator, and with the help of this function the value of the key is converted to a number. And loading IX with the value 8006 sets cursor to position 6. You can see it here. Here's 8000, 1, 2, 3, 4, 5, 6. So we have 8 columns. Yeah, saving the number. And this prints out the accumulator, so the result will be printed here. So the print accumulator will use two columns. And retrieving back the value, because the call here destroys the accumulator, we have to retrieve it back. Adding 30 to the number, this will build the ASCII number. And saving it back to register D. And here we're loading BC with 030, that means B is loaded with 8, which is used for the loop here, and C is 30, that's the I/O port. Same here. So clearing the accumulator, sending the start bit. So with the 0 is the start bit, waiting 3.3 milliseconds. That's the same function we have already discussed in the previous video. And okay, now retrieving back the accumulator with the saved value, filtering out the rest. Sending one bit, that's bit 0. C, so it's sending to the port 30. Waiting again 3.3 milliseconds, then shift right logical, which means we are shifting every bit one position to the right, so we get the next bit. Then repeating this 8 times, decrement jump on 0 will decrement register B. Let me try to simulate the send function in the simulator. So we want to send 30 to over the serial line, and we have to send it in reverse order, so the least significant bit first. 30 is also our serial line, so peripheral device out 30, bit 0, this one is our simulated serial line, oh my god, and 00 is our simulated accumulator. So the first bit we are going to send is a 0, so still 0. The second bit should also be a 0, still a 0. And the third should also be a 0 out, still 0. And now the fourth is coming. Fourth 0 is also 0. And now the first one should arrive. So here I send 1. And the second one, that was this one. And the next one should be a 0 again. 0. And the last one also a 0. So it's the next, it's also 0. And the function is finished. And finally, we are loading accumulator with 1, so we're sending the stop bit. The serial send line should be up again, and waiting at least 3.3 milliseconds, and we are done, jumping back to the loop. where we are again waiting for a key. Stay tuned if you're also interested in the Minimax source code, which has an Intel 8085 CPU. Otherwise, thank you for watching and see you in the next video. Bye bye. So this is the source code for the Minimax 8085. I've connected the Arduino to the serial in and serial out port of the Intel 8085 CPU. That's the out and that's the in. So your send, in this case the SOD, should always be high if unused. You will do this with set instruction mask. The set instruction mask will take the value of the accumulator and set the appropriate settings. So a quick review, we have your accumulator here, and with the SDE, serial data enable, if you set it to 1, it will send the value of SOD to the SOD port. Oh, I have an error here. So this is 2 to the power 4, 5, 6, 7. So the value here is 4, and this one is 8. 8 and 4 is 12, and that's a value which is needed for setting the SOD too high. Hexadecimal C is 12, so the next command is read instruction mask. This will not only read the instruction mask, but also the serial in. And the serial in is at bit 7, so we're filtering out the other bits. And if it's a 0, so that means there's a start bit received. If not, it will check if you have pressed the key. If no key is pressed, it will jump back to the loop here. Otherwise, it will read the value from the terminal, saving it to register C. And here we are sending the start bit. So here we are sending 1 with C, and here we are sending only a 0. So here's the call delay for 3.3 milliseconds. We have already covered that function in a previous video. It's the same function. And loading register with 8 for the loop. There are 8 bits to check. So restore saved value. Rotate right carry. So the bit 0 is moved to bit 7. So that's serial out. Saving the value and keeping only bit 7 and doing an OR. The for means set serial data enable, and we're programming the serial out with the value here in bit 7. Again, a call delay, decrement B, and we're doing this 8 times. I think it makes sense to demonstrate the send function in the simulator. So in this case, I want to send the value 30 to the serial over the serial port to the other device. And in serial communication, you send first the least significant bit. So this is the reverse order of this one. 0, 0, 0, 1, 1, 0, 0. What I've changed here, I've included an out to peripheral 0 just to demonstrate the accumulator in binary format. So that's our accumulator here in binary format. B is loaded with A, C is the character we want to send. So that's our 30 here. Rotate right carry, so we rotate to the right. Displaying it here in the window. Doing an AND with 8, 0, so it will be 0. Doing an OR with 40 to, this means enable the serial port, and it will send a 0 to the SOD because the 7th bit is 0. SOD is 0, decrementing B. Rotate right, so it rotated to the right. So the next value is again 0. That's our second 0 here. Okay, rotate right. You see here, this one has moved to this, and the second one had moved to 1. So this one is the one here. It will send a 1. And now 2 zeros left. And the last 0 is sent. So the next thing is sending the stop bit with a delay 3.3 milliseconds and jumping back to the loop. Checking again if the remote side has sent something. So if a start bit is received, we're going to receive here. Receive, here it is. So waiting 3.3 milliseconds, so we're waiting the end of the start bit. Setting register B with 8 and register C with 0. So this is a shortcut for setting carry and complement carrier. There's no clear carry flag, and this is a workaround. So you save 1 byte. Restoring the value of C and doing a remote accumulator or remote arithmetic right. So move every bit 1 position to the right. Saving again as the result to C and reading the value. Keep only bit 7, that's the SID, the serial in, and do a logical OR with C and saving it back to C. Calling and delay 3.3 milliseconds, decrementing B and doing this 8 times. So we're reading back the value from the remote side. So it makes sense again to demonstrate it in the simulator. The remote device sends 31, so it will send it with least significant bit, so it's in reverse order. Our out here is just to simulate the accumulator to display it in binary format. So reading the first value, so it will should be a 1. This device sends first a 1. So we get our 1 here. Move to the right. And the next value is a 0. So it's reading a 0. The next value is a second 0. Then you have your third 0. And you have two 1s, the first one. And the second one here. And two 0s again. And the last 0. See here, 31 received, 31. Then we have to wait for the stop bit and waiting 3.3 milliseconds and putting out the result to the terminal, checking if the send ready is free, and putting out the character we have received to the terminal, and jumping back to the main loop. Well, thank you for watching and see you in the next video. Bye bye.